In the first part of this lecture, we will concern with wheel space motion of molecular machines and in particular on molecular motors. We will see that the thermal ratchet model will explain most of the observations that have been done. In our discussion, we will be facing the experiment that is shown right over here. The motors are attached to a bead that is held in an optical tweezer. Now you bring the bead very close to the microtubule and you will see that the bead will be pulled by the motor that is attached to it. If you follow the time course of the force on the top right, you will see that the motor really makes steps. The force that the motor can apply is in the order of a few piconewton. On the bottom left, you see how the motor proceeds over time. It is obvious from those data that the motor really proceeds in a stepwise motion. So there are pauses in between where the signal is fairly noisy, pointing to the idea that the motor is diffusing at that moment. And then there's a step going, and actually the step width is 8 nanometer. From those kinds of experiments, we can learn how fast a motor is if you apply different forces to it. The result of such an experiment you see here on the top left. Here the force of a motor is displayed as a function of its speed, sliding speed of the motor. The data clearly show a correlation between the two parameters. Either the motor is very slow, then it can pull a high load, whereas when it's very fast, and the maximum speed here is 6,000 nanometer per second, then it cannot bear any force. We also can have a different look on that and look for the efficiency of the motor. The efficiency of the motor would be the work per ATP that it's burning for every step. For very low speeds, sliding speeds, the work is highest, amounting to roughly 60 piconewton nanometer, whereas for very fast motors, fast-moving motors, the efficiency drops down to 0. Now, those kind of experiments we would like to grasp in a model and explain from the underlying physical principles. Now, for the development of our understanding, we look into one typical motor, which is a thermal ratchet or the Feynman ratchet. The Feynman ratchet assumes that the motor is split into two pieces. One, you have a gearbox, which with the sawtooth panel, which allows only turning of the motor into one direction. Now this gearbox is connected through an axis to a pedal, which is hanging in a box that is filled with a gas at a given temperature. Now gas molecules will bump onto these pedals, eventually bringing it into some motion. Now, because the pedal is connected to this one-way gear, it's only allowed to move into one direction and not in the others. So hence, one could think about using such a motor and turning heat, so the temperature, into something useful, for example, lifting the weight on this motor. Such a motor certainly can work, yet it has to comply with the second law of thermodynamics, saying that entropy may only increase in such a process. So for a continuous machine, the energy can only be extracted if the temperature of the gas where the pedal is sitting in is higher than the temperature of the gearbox. And the explanation is fairly simple, because the temperature in the gearbox will also cause molecular motion and Brownian motion of the little spring that holds back the turning into one direction. Now, also from thermodynamics, we know we can determine the efficiency of such a machine, and we know that the efficiency is given by the temperature difference between the hot and the cold compartment divided by the temperature of the cold compartment. And only if there is a temperature difference, the efficiency is larger than zero. Okay, so hence what we learn from this Feynman ratchet, the Feynman ratchet cannot work without adding some additional energy. And that is something that we have to include in a refined model. So the refined model is what I display right over here. In the book it's called the S ratchet. In comparison now to the Feynman ratchet, this S ratchet, or our molecular machine, is now a 1D representation. So it's just a 1D rail where there are pranks which are normally retracted. Hence, the X position of this rail can move forth and back just by diffusion. However, if we release one of those pranks, the motion into one direction is prohibited. Yet for the release of one of the pranks, there's energy released. And this is exactly how this is happening in the molecular motor. So in the molecular motor, it will burn ATP from where it can feed directionality into the system. So the typical energy of ATP is what we learned, 24 kT. So it's very high as compared to the thermal energy. Now for the more detailed model of the ratchet, so we assume that there's a force pulling to the left, and the force is called little f. Then the motor makes steps of a step length L, so the distance between two pranks is a fixed number. And ATP is used to block the step to the left. So now let's analyze the motion of such a machine. In the first step, we assume that there is no force acting on this ratchet. And we're certainly only concerned about the motion of such a ratchet first just within two of those pranks. Now, because the motor is sitting in a thermal environment, it will move, and it will move just by diffusion. So we may ask now, how long does it take such a motor to move one of its steps between two pranks? Well, this is just given by diffusion. And from diffusion we know that the typical time scale for movement of a length L is given by the step time length is equal to L squared divided by 2D, where D is the diffusion constant. Now, having now the length scale and the time scale, we also can calculate the speed of such a motor at zero force, which is given by L divided by T step, and that equals 2D divided by L. As we calculated now, what is the speed of such a motor if there is no load? Now, in order to proceed, we need to look into a little bit more details about this motor mobility. And therefore we look into the probability to find the motor at a given position x if it starts at time equals to 0 at position 0 at a given time t later. Now this probability is just given by the diffusion law, and reads P of x and t is equal to e to the minus x squared divided by 4 dt times some prefactor which takes care of the scaling of the probability. Now, for not too large x and for long timescales, so certainly timescales longer than the step time length, this Gaussian curve is very flat. So the probability distribution will be just constant. So let's add some complexity. So far we considered there's no force and there are no bolts, and we found that the probability distribution to be at a given place is flat in space. What we also could have a look on is how the energy of the system changes with the position. And because there's no force, this is also flat. Now in the next step, let's add a finite force, yet forget about the bolts. Then the energy landscape will just linearly change with the movement of the motor. That's just the work done by the motor. So E is equal to F times X. Well, then we know that the probability of the position will change. Now what we just assume here is it changes in a Boltzmann-like way. That means the probability distribution will be peaked at 0, so at the last position, and will be proportional to e to the minus f times x divided by kBt. Hence, what we would expect is the motor just hangs on the right side and does not move anymore. What we do now is we add yet another step, and that is just assume that there is a finite force and the bolts might jump out. Now, by jumping out of one of the bolts, what will happen is that the energy given by F times X is decreased by the amount of energy that has been stored in the motors. So this is equal to minus E times the number of bolts that have been jumped out, and that I summarized here in this X divided by L, which just counts the number, so it's as an integer, which just counts the number of bolts that have jumped out until the position X. The result of this is that the energy now is a ratchet type energy landscape. So it rises up to the next bolt, and then there's a quick jump to negative values of the energy, and then it rises again. Already from this graphics, we can see that if the work that has to be done exceeds the energy of one of the bolts, so the jump down, then the motor will just stop. Only if the energy is higher as to the work that is done, the energy will really drop and the motor might proceed. Now, as a next step, we also can look into the probability that I can find the position of the motor. And again, this will be a sawtooth-like behavior, where between two of these pranks, it is given by something like the Boltzmann factor, minus f n times L minus x divided by kBt. So then we have the fully fledged model of this S ratchet. So we discussed the energy landscape, which is a sawtooth-like energy landscape. Between two pranks, it's governed by the work done by the motor, and when it jumps beyond one of the pranks, the energy of the spring is released, and we have a jump of the energy downward. Likewise, the probability distribution to find a motor at a given position is somehow peaked. It's highest close to the pranks and then just drops off until we reach the next prank. Now, from this graphical model that we just developed, we would like now to learn about the speed of the motor at various forces that are applied to it. Now, in order to calculate the speed of a motor, the only thing that is required is that we know the form of the probability distribution, from which we then can calculate the speed of the motor. Further, it's clear that because of the symmetry of the system, for every distant L, the problem just recurs. Hence, we only have to consider the position between x equals to 0 and x equals to L. Now, what we can realize is if we wait for time scales longer than the typical stepping time scale that we obtained for the diffusion, we know that the probability distribution is not time dependent anymore. And it will, the system will go into some equilibrium. Yet we should be a little bit careful to talk about equilibrium here, because equilibrium just means that the probability distribution to find a particle at a given position is constant, but this does not mean that the flux, which is the movement of particles, is equal to 0. The reason of this is that if particles are moving to the right, there are also particles that move to the left. So in that sense, the flux is not 0. Now what we could do now is we could calculate the total flux in such a system. So the total flux would be the change of the probability with time. That gives me the flux J of x. And that in our model should be due to diffusion. Between the two pranks, there's only diffusion that moves the motors forward and backward. Well, it's basically the first fixed law saying that the flux is equal to minus the diffusion constant times the gradient of the probability distribution P of x. Now, because of the load of the motor with the force F, there will be some general drift of the motor in the direction of the force. Hence, to this diffusional flux, we have to add a drift flux given by the drift velocity v drift times the probability P of x. Now, in statistical physics too, but also in diffusion, we learned that the drift velocity is equal to minus 1 divided by psi times the force, is the friction in the system. Now, very generally, Einstein told us that the friction is coupled to the diffusion constant. Hence, the drift velocity is given by minus d divided by kbt times the force, which is equivalent to the gradient in a potential, or the gradient of the energy landscape. Hence, putting everything together, we now have calculated the flux, the probability flux, as a function of x, and that is given by minus d times the gradient of P of x plus 1 divided by kbt times the probability P of x times the gradient of the potential. Thus far, we just considered the probability flux of the system. Yet we were interested in stationary solutions, which describe the energy, the equilibrium solutions. And for those, we needed to make sure that the gradient in the flux should be zero, meaning that there is no further pile up of the probability or the position of molecules occurring. Hence, using also that requirement, we finally come to the final equation that the gradient of the flux given by minus d times the gradient of p of x plus 1 divided by kBt p of x times the gradient of the potential must be equal to 0. Because this equation is so important, it also got a name, and that is the Smoluchowski equation. You also understand now how we get to our final solution. Because we have calculated the flux in the system. For that, you will need the probability distribution P of x. Yet the probability distribution P of x needs to solve the Smoluchowski equation. Hence, what we are going to do is we look for solutions of the Smoluchowski equations. That gives us a P of x, and from there we can calculate the flux. Okay, so let's do that. Here again a summary of what we found so far, the flux and the Smoluchowski equation, which both we only need to consider within one step length of the motor, because it's repetitive. Now, in order to obtain a solution of P of x, the easiest way is to use some trial functions, where we already have a very good idea, because we said that, well, the probability function will just drop down between the two pranks given by a Boltzmann factor. Hence, we have the probability distribution P of x is equal to e to the minus x divided by kBt times the force, times some constant factor which takes care of the normalization of the probability distribution. Now, before we go on, we also should look on additional requirements. And one additional requirement is that at the position L, the probability that the motor will be at that place has to be 0. The reason for that being, because then it's in the next slot and it made a step. Hence the probability will be beyond that point has to be 0. Yet this the trial solution that we have here does not comply to this requirement. So we have to repair the function. And one way to do that is that we now extend the exponential factor and letting the distance L be a special point. Hence, we use here the expression that the exponential factor now gets x exponent to the minus x minus L divided by kBt times f, which actually has a maximum and is 1 at the position L. So we subtract L and have the final trial solution. Now, if we check what are the requirements of the solution that we found here, is, well, we constructed that P of x vanishes at the bolt. So P of L is equal to 0. Further, we fill in our P of x trial function into the flux equation. And what we obtain is that the flux is equal to d times c divided by kBt times f. So it's a positive flux, not equal to zero. Well, since this flux is independent of the position, it also solves the Smoluchowski equation. Maybe just a small side mark. If we would have taken the earlier trial function, which we didn't make symmetric with respect to the bolts, we would have found that there's zero flux in the system. Okay, now we're ready to calculate the speed of the ratchet as a function of the temperature and the load. This is what we have been after. Now, first we need to calculate this constant c, which is equal to, or 1 divided by c is equal to the integral from 0 to L of p of x. Now, if you take this integral, you find that c to the minus 1 is equal to the equation that is shown right over here. So we can turn to calculate the speed of the ratchet. The speed of the ratchet v is equal to the length of one of those compartments divided by the time spent in one of those slots. And that is given by L divided by the total probability that the particles in one of those slots, which is equal to 1, divided by the flux, which is the change of the probability with time. Well, the flux we calculated is equal to dc divided by kBt times f. Hence, the velocity is equal to L times dc divided by kBt times f. Now, filling in also the constant, we finally derive the velocity and the speed of the motor as a function of the force, and kBt is equal to Fl divided by kBt squared times d divided by L divided by e to the power Fl divided by kBt minus Fl divided by kBt minus 1. So it's good, if you have such a complicated equation, to look for special cases. And the first one is what happens at small forces. Well, at small forces, the exponential factor we can linearize, and the exponent gives then 1 plus Fl divided by kBt plus a half Fl divided by kBt squared. Now, using this approximation, what we find is that the v, in that case, is the maximum speed, is equal to 2d divided by L. Hence, what we obtain back is our solution for the free diffusion behavior that we considered right in the beginning. So that's the maximum speed that the motor can move, and that is just given by the diffusion constant of the motor. The second limiting case is what happens at very large forces. Still, we have to consider that forces can be still large, yet the work, F times L, has to be smaller than the energy that we obtain back from the chemical reaction, the ATP burning. Well, in that case, the exponential factor is the main factor. And we see that the velocity then scales like e to the power minus Fl divided by kBt, which for large forces goes to 0. Hence, from our model, what we achieved is we can explain the experimental results. At very high forces, the speed will drop to 0. Whereas at very low forces, there's a maximum speed which the motor can move, and that is dictated by diffusion. Okay, just the summary on that part of lecture. So we looked for the ratchet's velocity against the load, we find this interesting behavior that it drops off, the speed drops off with the load in an exponential way. We further learned that the molecular machines translate energy into directed motion. We also learned that the description using the energy landscape is a useful description to understand the ratchet's motion, which also predicts that if the energy landscape is flat, there is no flux in such a system. Finally, we learned that there is a maximum speed of such a motor or ratchet, where the maximum speed is set by the diffusion constant of the motor.